slope fields. We have finished looking at the basic derivatives. We're moving on to the next big idea in calculus. Basically, we're going to say what happens when you're given the derivative and you need to find the function to start with. So for example, graph the family of functions where the derivative dy dx equals cosine x. We'll sit back and think, what function has the derivative of cosine x? Well, y equals sine x has a derivative whose cosine is x. Or, I'm sorry, whose derivative is cosine x. However, so does y equals sine x plus 4, because the 4, the derivative goes down to 0. So does y equal sine x plus 6, sine x plus, and you see we can get infinite amounts. So when we're graphing a family of functions that has a certain derivative, we need more than one possible answer. We need an infinite answers, and we need a way to show that. One way we can show that is with a bunch of graphs. And you can see that each of these graphs is sine x plus or minus a value with a shift up or down. And so this leads us to what's called slope fields. What we'll do is notice that the graph consists of a family of parallel curves. It should be no surprise to you, since the functions are all of the form sine x plus a constant. They're all vertical translations of the basic sine curve. A little less obvious is that we could have predicted the appearance of this family of curves from the differential equation itself. Looking at the equation, the derivative tells us slopes. We could produce the family of curves without even solving the differential equation, just by looking at those slopes. This is called slope fields. So what we're going to do is we're going to take our differential and we're going to look at lots of different points. We're going to look at calculating the slopes at different points. And we're going to do it over and over again. And we're going to create a lattice grid of slopes at those points. And we're not going to draw large pieces of the graph. We're just going to draw little linearizations at that point and see what's happening. So for example, we have the differential equation dy dx equals x plus y. Let's sketch a graph of this using slope fields. All right? It says to use a calculator to construct a slope field. I'm going to show you how to do it without, and then I'll show you a calculator program that you can download in class to calculate these or to draw these slope fields. So first off, our differential equation is dy dx equals x plus y. And we need to sketch a graph of the particular solution that passes through the point 2, 0. So first off, let's graph all the solutions, or a generalization of all the solutions, for dy dx equals x plus y. First off, good idea is to find your zero slopes. Where does x plus y equal 0? And x plus y equals 0 when y equals negative x. So any place y equals negative x, we need to draw a line, or a segment of a line, with a 0 slope. At y equals negative x. All right. Next thing we might want to do, what is happening when x equals 0? All right, go through what is happening at x equals 0. Well, when x is equal 0, dy dx equals y. So it's the y value. So here on the x-axis, when y equals 1, the slope is 1. When y equals 2, the slope is 2. So it gets steeper and it gets steeper and steeper as you go up. When y equals -1, the slope is -1, and it gets steeper and steeper going down as you go down. All right. What happens when y is 0? What happens when y is 0? Well, the slope is x. So here on the x-axis, where y is 0, the slope is whatever the x value is. Here it's 1, when x is 1. Here it's 2, so it's getting steeper and steeper. And it's hard to draw it much steeper than like 6 or 7. It doesn't show up very much. Now notice here we got two values. The slope is 1. And if you notice, they follow a pattern. So all the way through here, our slope is 1. All the way through here, our slope is -1. And you can verify that by just plugging in a few points. Right here, x is -3. I'm sorry, x is -2, y is 1. -2 plus 1 is -1. All right? Once you start seeing the pattern, you can start filling it up. And you'll notice we kind of got it flowing a general flow of a line right through here. It kind of flows out like this. All right, so to find a particular solution at 2, 0, I'm going to stop drawing this because it's going to get tedious. But you get the general idea. What we'll want to do here now, I'll show you graphing it, a program on our TI-84 called slope field with the subprogram z field. Input your derivative, x plus y, and it'll do the same thing that sketching by hand would do. So there's our derivative. You can see the general pattern we were starting to develop is developing, where we got right through here, slope of 1, and it's starting to curve off right through here. Okay. So let's grab that over. There's our slope field. Now when we want our particular solution that passes through 2, 0, find the point 2, 0, and see what's happening with the slopes there. You can see here it's kind of coming up. It's going to kind of curve here, and it's going to kind of flow at that point there. So there's our slope field, and we can see a particular solution there. So to do the slope field, you want to find where your zeros are. You want to graph your axes and kind of flow in the little slopes between there. Another thing you will be asked to do is some matching. All right, if you can match, you can use the same reasoning we had before to graph the slope fields. So for number 1 here, dy dx equals x minus y, where is y equal to 0? Or where is the slope equal to 0? Where is x minus y equals 0? Well, any place, x and y are the same. All right, so x, y are the same. Right through there. Okay. Those have slopes equal to 0. It's not showing them, but it shows how it changes from negative to positive. So number 1 is B. All right. For number 2, where is that one equal to 0? Well, x, y equals 0. Any place x or y is equal to 0. So any place on the x or y axis. All right. This one goes straight up or down on the x and y axis, so it's not that one. B we've already used. C looks like right here, where level slope is 0. Here it appears going up, going up. That one doesn't look like it quite works. So it must be D, and you can see slope is 0 here, and here we're approaching 0. So yeah, number 2 is D. All right, number 3, where is the slope equal to 0? Well, x over y equals 0. A fraction is only equal to 0 when the top is 0. So only when x equals 0 is this one equal to 0. And that would be here at A. X is equal to 0 on the y-axis. So this should be A. And here, y equals 0. Anything that makes the top 0, again, on the x-axis. Those are all our y equals 0. So that one's equal to C. So slope fields are a way for us to see general solutions, not specific ones, get an idea of what's happening with the graph. And if we were given a point on these, we could plot our point and scribble through and get a rough idea of what's happening to the graph at that point. And here's just a few examples. So slope fields.